The purpose of this video is to explain the operation of a bridge rectifier circuit wired using Locktronic components. Locktronic kits provide a modular solution to quickly and reliably connect components together. For example, a piece of wire connecting into the circuit between the metal pillars, it's very quick and it forms a reliable connection. The function of this circuit is to convert alternating current electricity, AC for short, which is the form of electricity that's generated in the national grid power stations and comes through into a house or office as 230 volt 3-pin mains. And we wish to convert alternating current to direct current form, AC to DC electricity. So why do we wish to do that? The reason is some products such as computers, laptops, smoke and heat detectors require DC power to function. Hence, in the UK, we require to convert 230 volt mains to a low voltage DC supply. In this case, we have a AC power supply which steps down the 230 volt mains to extra low voltage AC. For example, the one that we are using is 4 volts RMS. So why do we want to do that? The reason we do that is for safety purposes, to reduce the risk of electric shock. There must be risk assessments undertaken when working with electrical equipment. Electricity is a high risk hazard if it's not treated with respect, and to mitigate the risk of injury and experiment and wire circuits safely, we should use extra low voltage circuits below 50 volts AC. Our AC supply provides a nominal 4 volt RMS output. In this case, it's more akin to 4.4 volts RMS. Why is that? Well, if we look on our oscilloscope screen, we can see positive half cycles, negative half cycles of the input AC waveform going into our circuit here. If we measure on the scope, digital scope, we can see that the peak-to-peak voltage is 12.5 volts. If our supply is given out 4.4 volts root mean square RMS, if we multiply 4.4 by the square root of 2, we get 5.6 volts peak. That's 0 volts to plus and minus peaks. If we double that voltage, we get 12.4 volts peak to peak, which is reflected on the calculated value from an oscilloscope screen there. We have 4 diodes connected in a ring, such that diodes are conducting as pairs at any one time. On the positive half cycle of our AC waveform, one pair of diode is conducting and the other pair is switched off. On the negative half cycle of the AC waveform, the diode pairs switch over conducting. A diode passes current in one direction only, in this case forcing current to flow in one direction through our resistive load. So current is coming out plus terminal here, flowing through these wires, flowing through our 1K resistive load back to the diode ring and the AC supply. So this resistor is converting electric current to heat. If we move our probes over to the output waveform, we can see our output waveform on the scope screen never goes below 0 volts. It never goes negative. Hence, it is a DC output. However, the DC value is not constant. It still has the sinusoidal peaks in the waveform. The peak of this waveform will be 2 diode voltage drops below the peak of the AC input. If we remember back, the peak of our AC input was approximately 6.2 volts peak value. If we subtract from the 6.2 volts 2 diode drops, because we have quite a small current flowing through the 1K load resistor, then we'll assume that the diode drops are approximately 0.6 volts when they're conducting. If we subtract 0.6 volts from 6.2 volts, we get a 5 volt peak on our supply, and that is confirmed by the calculated peak to peak voltage on the oscilloscope screen, showing 5.1 volts peak to peak from 0 to the positive peak of our DC output. If we connect capacitors across our output 1 kilo ohm resistor, what happens is it tends to smooth out the waveform. In this case, it's not particularly smooth because it's quite a small value of capacitor in, it's 4.7 micros. Why do we put a capacitor across the 1 kilo ohm load? The reason we do it is it facilitates electron storage between the peaks and hence smooths out the waveform. The higher the value of capacitor, the smoother the output DC will be. With our 4.7 microfarad capacitor, it's not particularly smooth, and we can see that we still have a ripple voltage of more than 3 volts dictated by this peak to peak calculation here. Again, not particularly smooth, simply because the capacitor voltage is not big enough. If we replace 4.7 micros with a larger value of capacitor, so it's effectively got a bigger sink to store electrons, we now see that we get a relatively smooth value of DC coming out. It has very little ripple voltage on it. If we look here on the oscilloscope screen, it's got a ripple voltage of only 600 millivolts, and we can see on the screen that it's relatively smooth, although it's not a completely horizontal line. It still has a small amount, about 500 millivolts of ripple voltage on it. Our 1K load, what we can see, our 1K load is completing a circuit loop on the output of the diode ring. If we measure with a multimeter, it's measuring 4.3 volts DC voltage coming out. That matches up with the mean calculation of the voltage on the digital scope. If we divide 4.3 volts by 1 kilo ohm load, we can, via Ohm's law, voltage divided by resistance, we can calculate the expected current in this current loop should be 4.3 volts divided by 1000 ohms. That should give us 4.3 milliamps. So if we disconnect our meter from this point here, which is reading voltage, we change the probe setting to use a different circuit inside because we now want to measure current. We want to move over to the 20 ohm range. To measure current, we require to break into the circuit. We'll take that wire out and we'll now measure the current flowing through the circuit. What we can see on the screen is it measures the current as 4.2 milliamps, which matches up with the expected current from theory of Ohm's law theory of 4.3 volts divided by 1000 ohms should give us 4.3 milliamps. We're measuring 4.2 milliamps due to the fact that this is a nominal value of 1000, so given a particular tolerance it won't be exactly 1000, and it also depends on the accuracy of our digital meter as well. Because we're drawing a load current from this circuit, it results in a slightly lower value of resultant DC output because there's a certain source resistance in this circuit. If we remove the 1 kilo ohm load, we can see that we now have zero load current flowing and we get out a smooth DC line. If we look at the mean value, we now see that it's reading 5.2, which is what we expected out from the DC output from the diode ring. 6.2 volts minus 0.6 volts voltage drop across each of the conducting diodes in the pairs gives us 5 volts, which is what we're getting out as a smooth line out of the bridge rectifier. We're getting smooth DC out of it now. Thank you for watching and please subscribe.